a lot.
Yes, sir. Yes.
Okay, I'm going to start the recording now. Okay, good. Thanks. Okay, so we are talking about vectors and tensor operations. These are the basis vectors E1, E2, E3. And the unit vectors have, they have unit magnitude. So the magnitude is equal to 1. And we can write this E1, E2, E3 as either Ex, Ey, Ez, Er, E theta, Ez, or Er, E theta, E phi. So this is Cartesian coordinates, cylindrical coordinates, spherical coordinates, and like that. Now for all these cases, if you take the dot product between two unit vectors, Ei and Ej, where I could go from 1 to 3 and j could go from 1 to 3, it could take on one value. This is not a summation. Then the dot product is given by Kronecker delta, which is defined here. It is 1 if I is equal to j and 0 if I is not equal to j. And the cross product between any two unit vectors is the alternating unit tensor times Ek, where this alternating unit tensor is 0 if any index is repeated. So, if it is 1, 1, 2, then epsilon is 0. Epsilon of 1, 1, 2 is 0. It is 1 if the indices are in this order, and it is equal to -1 if the indices are in the reverse order. And using this, we can do all sorts of operations, and we saw a couple of examples. But mainly we said, okay, we'll write the vector as a scalar times a unit vector. And then you can just, for any operation, let's say a dot product, you will always take the dot between the unit vectors and take the scalars out of the brackets. And then the dot product will be given by the Kronecker delta. So you have Ui, Vj, delta Ij. Since I is repeated and j is repeated, this is actually a double summation over I and j, both going from 1 to 3. But all the terms in which I is not equal to j are equal to 0. So then this just becomes Ui Vi by putting j equal to I, for which delta is just equal to 1. And then we also looked at a generalization of this idea of a vector. So here you have a scalar and one direction vector. A tensor or a second order tensor is a scalar and then two directions like this, where this is a unit dyad. And then once we have defined this, these two vectors have a dyadic product between them. That means they're just stuck together. There's nothing, no further operation is needed. And of course, Ei, Ej is not equal to Ej, Ei. And this is one example that we looked at. So if you take a dot product between a vector and a tensor, then you can write it in component form. There's Vi, Ei dotted with TKL, EK, EL. Again, the dot is always between the two closest unit vectors. So when we take that dot product, we get delta IK. This is what it is. And then you put, since delta ik is 0 unless k is equal to I, so you simply put k equal to I over here. So then this will give you a vector. So many people talk about the tensor as being a linear vector function because given a vector v, we have got a new vector. Let's call that as u. So this is a function which operates on a vector and gives you another vector. And it's also linear. That is, if you multiply v by a scalar, then u will also be multiplied by the same scalar. So there's a linearity in there. And of course, you can have many more operations. So that's what I'm going to do. I'll look at some more tensor operations and definitions of different types of tensors next. So any questions? Anybody have any questions? So today is the 5th of August and we are in lecture number 6. So let's now look at a few more vector and tensor operations. Okay. So supposing you want to take dot product between two tensors. So let's say A is one tensor and B is another tensor, and you want to take the dot product between them. This is like matrix multiplication. So you have Aij dotted with Bkn. And here again, always the dot product is between the two closest unit vectors. The scalars can be pulled out. So you have Aij Bkl and delta Jk because of the dot product, and then Ei El. So this is what you have, and then since this delta Jk is 0 unless k is equal to j, so wherever we have k, we'll put it equal to j. That's the only non-zero term that will remain. So here you have Aij Bjl Ei El. So you see we get a tensor when we essentially multiply, take a dot product between two tensors. Then there is another type of product which is called the double dot product. Again between tensors. This is only defined for tensors. And what does this say? Let's say we take the same two tensors, A double dot B, and this again is the same. But instead of one dot, we now have two dot products to be done. Now the formula is the same. First take the first dot product between the two closest vectors, and then the second dot product between the next two closest. So when we see this, you get this is Aij Bkl, and now you'll have delta Jk as before, and then we also have delta IL. So in here we must put k equal to j and L equal to I. So you just get Aij. Now k is equal to j, so that is Bj, and L is equal to I, so it's Bji. So this is what is the double dot product between two, and what you end up with is a scalar quantity. Now I've said this in the last class, but let me just say it one more time. The only things that you have to remember: one, whenever you have any dot product or cross product, it is always between the two unit vectors which are closest to that dot or cross. So that is one point. And the second point is, please make sure that all your indices are named in a different way. That's why I've used I, J, K, L. If there were more indices, I can go to P, Q, R, S, T, whatever. But if you use, it's just like when you're solving an equation, for each quantity, you must have a different variable. Same way here, for each index, you must have a different variable. Otherwise, there will be confusion. So that was about,
Hello, sir. Can you
yeah,
please elaborate that first term, that what you have said right now, the first one?
that the dot product is always between the closest unit vectors. You're saying that? Is that what
Yes, sir.
you?
Yes, sir. Yes, sir.
So this is what I mean, that let's say this is the dot product. I've written down the tensor A and the tensor B over here. So when I take the dot product, this unit vector is closest to the dot and this unit vector is closest to this dot. That's why I'm taking the dot product between these two and not between I and L. Is that clear?
Okay. Okay. Okay.
Mhm. And even over here, when I have to take two dot products, I first take between the two unit vectors closest to the double dot, and then we take off the unit vectors which are remaining. So, because if you had taken, let's say, dot product between EJ and EL, then you'll get the wrong answer. It has to be between J and K. And if you do
Okay.
this, then this is just like how you have learned how to do matrix multiplication. This is exactly what it is. So you multiply two 3 by 3 matrices, you will get another 3 by 3 matrix, and whatever this formula gives you is the correct answer. Remember that in this, there is a summation, there's actually three summations. Summation over I because I is repeated, summation over j because j is repeated, and summation over L because L is repeated. So there are three summation signs which I'm not writing down. We are following the summation convention. So anytime an index is repeated, let's say for example j is repeated, that means this is actually a summation over j going from 1 to 3. Similarly, summation over I going from 1 to 3. Okay, then I want to define a few tensors. So we have a unit tensor. We usually call it as I, and this is defined as just EI, EI. If you have to write it in matrix form, it's just 1 0 0 0 1 0. This is known as a unit tensor. Then we want to define, and a property of the unit tensor, of course, is that A dotted with I will always give you I. And this you can test for, I'm sorry, will always give you A. So this is the same thing, like if you multiply any number with 1, you'll get back the original number. Same way here, if you multiply any matrix with the unit matrix, you'll get back the original one. Then another operation that is important is known as transpose of a tensor. And is denoted as, let's say, A transpose. That is what it's denoted as. And so if you look at this, if we have Aij, Ei, Ej, and we take a transpose of it, then this is simply equal to, what you have to do is when you transpose it, then you interchange rows and columns. And one way of doing it is to interchange the order of this dyadic product. So what we can do is we can just simply write Aij, Ej, Ei. So this is the transpose of A. So it's Aij, Ej, Ei. So these unit vectors have been interchanged. But you know, what we call these things makes no difference. So this is exactly the same as writing Aj, Ei, Ej, and it is also exactly the same as writing APQ, EQ, EP. So it doesn't matter what you call it. There's a summation of P going from 1 to 3 and Q going from 1 to 3. So all of these will give you the same answer. So this is what is the transpose of a tensor. Then another operation is, or a property you can say, is trace of a tensor. It's denoted as TR of, let's say, T, if T is the tensor. Then this is just equal to P I. Okay. So since I'm the one talking all the time, now let somebody else tell me, what does this mean? Physically, what have I written down? When I say TII, what does that mean?
So normally trace means the diagonal elements of a matrix. So similarly, this should similar. So,
So is it just the diagonal elements? What is the precise?
so the sum of the diagonal elements. Sum of the
Sum.
diagonal elements.
So now if I write it like this, is this equation correct? Does it make sense?
So
TII,
summation, we need summation.
but since we are following, so that's why I wanted to just bring that to your notice. Since we are following the summation convention, notice that the I is repeated. So this is actually a summation of I going from 1 to 3. So if you expand it into the component forms, this is just T11 plus T22 plus T33.
And T.
Correct?
Yes, sir.
Yes, sir.
Yes, sir.
And that is nothing but the sum of the diagonal elements. Okay. Hey, Vivek, you're here?
Yes, sir, I am here. I'm good, sir.
I've seen you before.
Actually, send you a mail about a link, so I found it out and I joined.
Okay, okay.
Yes.
Very good. And so now, once we know all these things, then I can just tell you a couple of identities. Identities means that they are true for all tensors. So one identity is that trace of tau is just equal to, trace of t is just equal to t double dotted with I. So if you take the double dot product of t with the unit tensor, that is the same as taking the trace. And if you take trace of A dot B, then this is the same thing as A double dot B. And you can, we have given all the definitions, and so you can easily derive these by putting them into component form on both sides. If you put into component form, you'll see, in fact, you'll get the correct answer. So we already know what is A double dot B, that is given in here. So we already know the formula for A double dot B, and we also know the formula for A dot B. Now you can take the trace of A dot B and then show that in fact the two are equal. So that I leave to you. And then the final thing that I wanted to define is determinant of a tensor. So this is for a we are always dealing with 3x3 systems. So determinant of any tensor T is just given by, do you know the formula for this? Well, I know that everyone knows how to do it. Take this column and then multiply those two out and so forth. But you can write it in a very compact form as just in terms of the alternating unit tensor epsilon ijk T1i T2j T3. Again, you can check. And when you take the determinant, again, it's a scalar quantity. Okay. So with this, this is a sort of brief review of various tensor operations. And so with this, I will end the vector and tensor operations. That is just the algebra part. Then let me talk a little bit about differential operations. So we have just so far been, you can say we've been doing the algebra, you take dot product and multiplying things together. But now supposing you want to take a derivative, so you can define something called a gradient operator. So for all the algebraic operations, we had dot products and cross products, and then everything else followed from there. Here, the key operation is the gradient operation. That is the del operator, nabla or del. This is the inverted triangle. And what it means is this is just EI del by del xi. This is what it means. This is nothing but E1 del by del x1 plus E2 del by del x2 plus E3 del by del x3. Of course, there is something missing over here. So some quantity will come here. So you have to take gradient of some quantity. Okay. So let's say if you wanted to just take of any function f, then del of f is just going to be E1 del f by del x1 plus E2 okay, so this is what you get. So this is nothing but gradient of a scalar. Now, if we look at for vectors, supposing we want to take gradient of a vector, how will we do it? Well, if we write it down, in that blank space, we just put the vector v. And then this is just so over here I'm saying I'm only looking at Cartesian coordinates. So this is not for cylindrical coordinates and all that. That will come a little later. So this is only for x, y, z coordinates. So 1, 2, 3 is just x, y, and z. So this, when we take gradient of v, so we have ei del of del xi, and then that operates on vj ej. So that's my vector v. So putting it in component form. Now again, as before, we simply take all the unit vectors on one side, and then the derivative is only of the scalar quantity. So this is just ei, ej, and then these are all constants, right? Ex, ey, ez, they're all constants, so you can't take derivatives of them, but velocity may be, v may be changing. So we have to take derivative of that quantity. So that's why you get del Vj by del xi. So you can see that the gradient of a vector gives you a tensor. That's why we have a velocity gradient tensor. So if V is a velocity vector, then this is the velocity gradient tensor. Then we can think of also doing another operation called divergence. And I'll do divergence of a, you can do of both vectors and tensors, but I'll do divergence of a tensor. And this is, divergence means del dotted and the tensor is T. So this can be written as EI del by del xi dotted with T KL EK EL. Again, notice I've used all different indices for each one of them. Now, you know, the dot, I will now have to take a dot product. So the dot product is between the two closest unit vectors, which are these two. And then the derivative is of the scalar quantity. So what I will get is, for the dot product, I will get delta ik. The vector remains as it is, EL. And then I have the derivative of the scalar quantity, del pkl by del xi. Now these all terms where I is not equal to k will be 0. So let's put k equal to I. So then I will get del of TIL by del xi times EL. And this is a vector. So if you take divergence of a tensor, you will get a vector. And the final thing I'd like to, oh no, not final, but last two things I want to tell you is curl of a vector. So it's again the same operation. Over here, in this, we are taking, for when we take the gradient, we are actually doing a dyadic product. That's why we generate this unit dyads. Here, we are taking a dot product. So that's why, you know, you'll get this delta and there's reduction in order. And when you do curl, you are taking a cross product. That's the example of each of the operations plus derivative. So if you take curl of V, so you're taking a cross product. Again, the del operator is the same, del EI del by del xi. And this is crossed with Vj, Vj. Okay. And then this, again, the cross product is between the unit vectors. And the derivative is of the scalar quantity. So when you do EI cross EJ, so the cross product gives us epsilon ijk ek. That's the Kronecker, the alternating unit tensor times ek. This is what is the definition of the cross product. And then you take del Vj by del xi. So this is your curl. And you can see that the curl of a vector is a vector. You know, this you can't simplify it any further. If you want, you can expand it and you will get the result you will get is exactly what you would have calculated using other methods. Then the last derivative is, which we'll come across quite often, is called Laplacian of a vector. This Laplacian is denoted as del squared. So that's why it's del squared of v, where v is a vector. And really what this del squared means is nothing but this, the actual meaning of it is it's a divergence of gradient of the vector. This is what is del squared. Del squared is just this operator dotted with itself. So when you do this, this is EI del by del XI, and then dotted with EJ del by del XJ, and then operated on, so there's no dot over here, just see it's gradient of V. So then here it is just VK EK. So when we take this out, you see that this dot product is between these unit vectors, and here it is. So this gives us delta ij for the dot product. Then these two derivatives will give us a second derivative. So del squared del xi del xj, and this is operating on vk and multiplied by the unit vector. So Laplacian of a vector is again a vector. Now this can of course be simplified, and all the terms where I is not equal to j will be 0. So I put j equal to I. So that gives us del squared vk, and I'm going to keep it in this format, just to remind us that this is actually a summation of I going from 1 to 3 and k going from 1 to 3. So that's just a brief summary of operations related to, sort of, you can say this is the calculus, the derivatives. But you know what, one thing that I left out was what happens if you want to deal with cylindrical coordinates. Well, you know, everything that we did before this, all these things that we have done, that is not these things, but all these things that we have done, all the vector operations, tensor operations, all these things, they are all valid. So up to here, up to this point, it doesn't matter whether it's Cartesian, cylindrical, spherical coordinates, all these equations are valid. They're whether you have 1, 2, 3 is XYZ or R theta phi or R theta Z, it doesn't matter. But when you talk about differential operations, then these formula I gave you are only for Cartesian coordinates, that is the XYZ coordinate system. And why is that? Well, I'm going to just do one example to illustrate this. And the example I'm going to do is to find divergence of V in cylindrical coordinates. And you'll see that this is not the same as the formula that you would get from the thing above. Cylindrical coordinates are R, theta, and Z. Okay. Now let's just look at the R and theta coordinates. How do they relate to the X and Y? So supposing this is my X axis and this is my Y axis, and supposing this is my unit vector Ex, and let's say this is my unit vector Ey. Okay. Okay. Now we also can define R, theta, and phi. So in cylindrical coordinates, the way it works is a line here, and this is, let's say, some point. So then this is the position vector r, and this angle with the x-axis is called theta. So this is the relationship between x, y, r, theta. And then a unit vector in the direction of r is er, and then a unit vector that is normal to er, and you can say in the tangential direction or in the theta direction, is e theta. So these are the unit vectors. Now you can see that for given a value of theta, I can always express er and e theta in terms of the unit vectors ex and ey. Now, since you are all so good at math, so I'm going to write down this result and you can check it yourself. So I'm just writing down this simple sort of coordinate geometry type thing where I'm writing down er is ex cos theta plus ey sin theta. So if you take the components of er in the two directions, ex and ey, then you can see that this dotted line is nothing but, so this line over here. So er will be this ex cos theta and then this times sin theta. You can say that this, what should I say? You can look at the limiting cases. You can see that when theta is equal to 0, er is equal to ex, and when theta is 90, er is equal to ey. So that is one check to see that the formula is correct. And similarly for e theta also you can calculate, and that will be, it will be just ey cos theta minus ex sin theta. Again, you can see this when theta is equal to 0, e theta is in the direction of ey, and when theta is 90, e theta is in the opposite direction to ex. So this is the relationship. So, as a function of theta, er and e theta will change. And from this, we can easily find out that supposing you want to calculate the derivative d of er by d theta, then using the above formula, I will get this is just nothing but minus ex sine of theta, because the derivative of cos theta is sine theta. Derivative of ex is 0. That is a constant vector. And then here, derivative of sine theta is cos theta. So what is this equal to? Minus ex sine theta plus ey cos theta. Well, look, this is nothing but e theta. So rate of change of er with e theta is just, the er with theta is just equal to e theta. And similarly, I can write down the derivative of del e theta by del theta. And that will be, derivative of this is minus of ey sine theta, and derivative of sine theta is cos theta, so this is minus ex of cos theta, and this is just equal to minus er. So these are the important results for us. So what we find is that d of er by d theta is equal to e theta, and del of e theta by del theta is equal to minus er. Of course, all the other derivatives are 0. And then, of course, with respect to, and of course, the derivative with respect to Ez is also 0, and all, so that I'm not writing down. So these are the only two non-zero derivatives of the unit vectors. So this is really the main issue, that when we are taking derivatives, we have to take this into account. So when we want to take, it turns out that the del operator also in cylindrical coordinates is different from the one in Cartesian coordinates. And the del operator in cylindrical coordinates is given by ER del by del R, which is similar to what we have. But for theta, we have E theta by R del by del theta, and then Ez del by del Z. Now, you can easily derive this. So in the notes, if you look in the notes, I've given the full derivation of how to calculate, excuse me, how to calculate this del operator in cylindrical coordinates. It's there in the notes. So let's say del is given by this. V in cylindrical coordinates is just VR, ER plus V theta, E theta plus VZ, EZ. Okay. And so what is the divergence of V equal to? Well, it is this dotted with so now there are two things. There are two things here. And what I'll do is I will look at the derivative and the dot product separately. So when we look at the derivatives, so first we'll take the derivatives and then the dot product. So if you look at the derivative, if you take with respect to R, then the only thing that varies with R is VR, V theta and VZ. ER, E theta, EZ don't depend on R. Similarly, if you look at Z, the derivative of ER with respect to Z, E theta with respect to Z, and EZ with respect to Z are 0. So then we don't have to worry about that at all. So for these two terms, we simply do exactly the same as we did for the Cartesian coordinates. So you simply take the dot products and then the derivative. So what you find is the dot product of, let's say, the first term of this term. If I take the dot product with this, ER dot ER will give me 1. So that we'll take. But ER dot E theta is 0 and ER dot EZ is 0. So the first term will give you only 1. And so this is just equal to, I'll just write it as for completeness, ER dot ER. And we'll have del VR by del R. Then let's look at the last term. Here again is the same thing. This dot product will be 0, this dot product will be 0, and this dot product will give you 1. So for the last one, again I have just EZ dotted with EZ del VZ by del Z. So these two are straightforward. Now here, when we look at the theta term, we have a little bit of some trickiness, because you have to take the derivative of both things. So I'm going to write it as plus, I'm going to just keep the dot product out, E theta by R, and I'll take a dot product and then I'll take derivatives. Okay, so first one will be, I'll have ER del VR by del theta. Okay, so that is taking the derivative of the scalar part plus VR into del ER by del theta. You see, Now I'm getting for the first term, I'm getting two terms. One is the derivative with respect to the scalar, and the other is the derivative with respect to the vector. And then for this, for the second term, I will get so I'll write it here, plus again derivative with respect to the scalar part, so I'll get e theta del v theta by del theta, and then I'll get a derivative with respect to the this is e theta by r, no sorry, r is already taken care of, sorry. So just del by del theta I'm doing, e theta by r is outside. So this is the derivative with respect to theta of the scalar part, and now of the vector part, that will be plus v theta del e theta by del theta. And then for the z term, actually, there is no derivative with respect to Ez. So the only thing that we have to do is del Vz by del theta. So then you just have plus Ez del Vz by del theta. Okay. So does anybody have any question on what I've done here? Is this clear? So essentially what I've done is I've just done del by del theta of these terms, and it turns out that in this bracket, not only do we have to take derivatives of the scalar quantities Vr, V theta and Vz, which are these derivative of scalar quantities, but we also need to take derivatives of the vectors Er and E theta. Of course, no need to take derivative of Ez, but here are the derivatives of Er and E theta. So now the first two terms are simple, Vr by del R plus del Vz by del Z. Then plus, now when I look inside here, E theta, the first term, this term, E theta dot Er, so obviously this term is just 0. What is del Er by del theta? Del of Er by del theta is E theta. And E theta dot E theta is 1. So this will give me Vr by R. Since this term is equal to E theta. Okay. Then we look at this term, E theta dot E theta is 1. So you will here just get del V theta 1 by R del V theta by. And then finally you have this term here, and the derivative of this is just minus Er, and then if you take E theta dot Er, that is 0. Also E theta dot Ez is 0. So that's it. There are no more terms. So all of these are 0. So we essentially have this term equal to 0 and this term also equal to 0. So now we have only these 4 terms that are remaining. And now we can see that this is Vr by R and del Vr by del R. We can combine them, and this is the formula that you will usually find in the books. Okay. So this is the only thing we have to be careful about, that when you're taking derivative operations, then there are some which are, in some cases, the unit vector itself may be dependent on the variable. So you will get additional terms which you have to account for. Okay. Is this fine? Okay. I just want to end with and show you the last thing, so that will sort of be the end of the vectors and tensors business. And that is this idea of integral theorems. They're not, I'm not going to give the derivation, but I just sort of mention this, and this will be there in the notes. There are three very important integral theorems. That is, one is called the divergence theorem, and I'm sure you have come across this before in many places, which basically converts a volume integral into a surface integral. So if you have divergence of a vector over any volume V, then it just becomes V dot n into the surface integral, where n is a unit normal vector pointing outward. This is normal to the surface. So, you know, this is normal to the surface S. So this is one important theorem. And similarly, there is another important one called Stokes' curl theorem. And here, you know, you reduce a surface integral into a line integral. So if you have curl of any vector dotted with n, where n is the unit normal to the surface, integrated over the entire surface, then this quantity can be simply obtained as the line integral over the curve C of v dot t, where t is a unit tangent vector to the curve. And really, the directions of n and t are not independent. So if n is pointing along the thumb of your right hand, so it's the right hand rule again. So if the normal vector is along the thumb, then the fingers point along the direction t. And the last thing I wanted to tell you is this so-called Reynolds transport theorem. Again, same Reynolds number person has derived this. And it says that supposing you have something called a material volume. What is a material volume? A material volume, let's say if you have a fluid or any continuum, then if you pick a volume in there and then you follow those particles which are within the volume at all times, then that is called a material volume. So the particles within the material volume remain the same. And SM is a material surface. That means whatever particles form the surface always remain on that surface. So in other words, the surface moves with the continuum. So then for this, where n is the unit normal to that, then the time derivative. So this is like, you know, taking a derivative of an integral. So if you take time derivative of the integral of any quantity psi, psi could be scalar, vector, tensor, anything, then this is simply equal to the time derivative of psi itself, partial derivative, integrated over the volume, plus the surface integral of psi into v dot n. Now here v is not a vector, but this is the velocity of the continuum. Okay. So in a sense, in a very short time, I've given you a quick overview of vectors, how to take derivatives, and some few integral theorems. I'm assuming that you know all of this, you have seen it all before. That's why I went a little fast. If you have any questions or doubts, then please ask me in the next class. And with this, I'll end. Perhaps later today, I will be putting the homework assignment up. And so you can have a look at it. As I had mentioned, I want you all to attempt the homework assignments as groups. So please inform Nilatri about the groups. And we'll do the grading. So each group will get a single grade. Okay? So, but each group should work independently. I think that's what Niladri also has said, that we want you to try out things so that you will be able to learn some of these. Okay. So